for you.
All right, go.
Well, okay, only 5 minutes late. Good, good. Thanks for coming, everybody. Today we have David Kaplan. Very happy to have David. He's been visiting for a couple of weeks. You're still around tomorrow, right?
Yeah.
So if you have more questions for David after this talk, you can cross the street and look for him at the Joseph Stefan Institute. And today David is going to tell us about shadow matter. Please.
Yeah. Hi, everybody. This is, I understand this is a mixed audience, and so let's just relax and enjoy ourselves and interrupt me if you don't understand anything. I'm going to start with very basic things about quantum mechanics, and then we'll dive into quantum field theory, and we'll talk about this set of ideas that I've been thinking about the last few years with a number of colleagues. Okay. The technical thing that I'm doing, and if it's too technical, ignore this slide. It's taking gauge theories, and gauge theories are very important in quantum field theory because they're supposed to be the underpinning of electromagnetism and gravity, all of the things that we understand in a classical way. And there should be some quantum field theory because quantum field theory seems to be the underlying principle of everything so far. There should be quantum field theories that give us Maxwell's equation, give us GR, things like that. And so I'm going to talk about a little bit about how that's done and the fact that if you do it in a pedestrian way, we can get some additional phenomena that people don't discuss. So first, how do we get Newton's laws, or how do we get the classical equations of motion? Well, we can get them starting in, I think, the 18th century. You can construct an action with a Lagrangian, and if you minimize the path of coordinates for that act that minimizes that action, you discover equations of motion. That's classically how we can get Newton's laws. And then you can also, instead of using a Lagrangian, you can use a Hamiltonian, and instead of thinking about q and its time derivative, q being a coordinate, you can think about a conjugate variable, the momentum p. And this is a nice stepping stone to quantum mechanics. So if you take a coordinate and its conjugate, call them operators, and then have a non-trivial commutation relation, x and p, then you get the classical equations of motion from Schrödinger's equation. So when I take a derivative of, let's say, the expectation value, yeah, is there a pointer or something? Okay, I won't shine the laser at you. So take the operator and put a little bracket. This is the expectation value. If you take a derivative of the expectation value, Schrödinger's equation, time evolves either this part of the state or this state, and you get a commutator. And written heuristically, that commutator removes a p, and it gives you dh dp. Or a time derivative of the p operator gives you minus dh dx. And for a Hamiltonian of a single particle in a potential, that says x dot is p over m in expectation value, and p dot is a force. So you get F equals ma automatically from quantum mechanics. You just have to make sure you constructed the correct quantum Hamiltonian with these being operators. Now, you can have examples where slightly weird things happen, and the simplest example is, say, if you have two particles with only a force between them. So there's no background potential, there's just the relative distance giving you the strength of that force, and therefore the potential. And with that Hamiltonian, I can switch to center of mass coordinates, and I get a Hamiltonian for both the center of mass momentum and the relative momentum. And then there's this q. Q is the relative position of the two particles. The overall position doesn't matter. So momentum is conserved in this situation, but it also means that there's a quantum number, there's a property of the state which is in some sense irrelevant. The total momentum p commutes with the Hamiltonian because the conjugate doesn't appear in the Hamiltonian. There's no capital Q here. So because it commutes, that means you can take your energy eigenstates and also make them eigenstates of the total momentum of the system. So you have two particles, they're doing something, they could also be moving at some velocity. You wouldn't know if you have no bearing on the center of mass position. So you can think of the world, this world where total momentum is conserved, as one which is in some eigenstate of the total momentum, but we don't know what it is. It could be that you decide, for simplicity, that the total momentum will be 0, and you can ignore it completely, but it could also be some other value, or you don't even need to be in an eigenstate of the total momentum. You could have some uncertainty in the total momentum, but we cannot detect it. We are not measuring it if we are part of this Hamiltonian which doesn't have capital Q in it. Now you might say that, well, who cares? That's a quantity that we can't measure. It's not physical. I don't care. Forget it. But you could also build a Hamiltonian that has another term with the total momentum times some other potential. So depending on the total momentum of the system, the potential between the two particles changes. So now it matters in the sense that while the momentum is still commuting with the Hamiltonian, and so you can be in an eigenstate of the total momentum or not, this term actually matters. This cares about what state you're in, and we measure the total potential of Q between the two particles. And if we knew this was the Hamiltonian of the world, it would tell us something about what that P is. And if we're not in an eigenstate of P, we're in some combination, but there's, say, some average value of the total momentum. When we measure it, we entangle ourselves with the outcome, and we would measure some value of P, and we measure that by measuring the total potential. So even though capital P commutes with H, it has physical consequences. So that's the whole message I want to say.
So if you're in an eigenstate of P, then you might as well just make P a number.
Yeah, you might as well just make P a number. That's right.
And then it looks.
Then you would never know, because we live in one universe where we make one measurement, and we entangle ourselves with the outcome of that. That's right.
So it only gets weird if you say we're in a linear superposition.
The only weird thing about it is that there's a distinction between the initial condition and the experience of the world. So the initial condition can be a linear combination of these states, but when you measure it, apologies if you hate many worlds, but if you measure it, then you get entangled with that outcome, and so now your wave function is split between all of those worlds. You measure it at some accuracy. It'll have some average value, won't know what it is, and then yes, whatever that is your world, and you could decide that that's the world. There's no other variable. I don't care about it. Absolutely. So you personally wouldn't be able to tell the difference because of that physical consequence. You can make this as complicated as you like, a function of capital P and Q, and you can get very different types of behavior, but ultimately you will entangle yourself with the outcome. So yes, your experience, you wouldn't know that this is happening. Unless, well, you still wouldn't know, but if this V bar broke some symmetries, then you would discover that the symmetry is broken, and the breaking of the symmetry will depend on what value of P you have, how big it is or small it is. But yes, you wouldn't be able to tell that I could construct this operator of the universe. Just like I can't see beyond a horizon. So in electromagnetism, we have a classical action, and we write the classical action in some fancy way, and we write it in that way, first of all, because it's Lorentz invariant, but second, because when you vary this particular action with respect to the vector potential A mu, you get 4 equations. The A0 variation gives you Gauss's law, and the variation of the action with respect to the vector potential gives you Ampere's law. And so you can construct this action in classical electromagnetism, minimize it with respect to the vector potential, and get all of Maxwell's equations. And then if you want to go to a Hamiltonian language, you construct the conjugate momenta in a standard way. You discover the conjugate momentum for A, the vector potential is the electric field, but there's no A0 dot appearing in here. So there's no conjugate momentum for the scalar potential. So what does that mean? Well, I can construct the Hamiltonian, but I have no conjugate for A0 in the Hamiltonian. And what we know about electromagnetism is that we have some freedom to define the vector potential. There's a gauge freedom. And since this object doesn't commute or doesn't have anybody with non-trivial commutators, I can just choose the value of this object, and I will choose the simplest thing, which is A0 equals to 0. That's called Weil gauge. And when I do that, the remaining objects I have commutation relations with the A vector. So this is now my quantum mechanics with 3 positions or coordinate fields and their conjugates, the electric field. And now I can do the trick using Schrödinger's equation to get the classical equations of motion. The time derivative of A just gives me an expectation value of the commutator of A and the Hamiltonian. That just gives me E. And the time derivative of the electric field, the commutator of H and E, gives me del cross B plus J, Ampere's law, automatically from Schrödinger's equation and my choice of Hamiltonian. It does not give me Gauss's law. And one simple way you can see it shouldn't give me Gauss's law is that these are equations with time derivatives, and this is not. This is just a fixed equation for the electric field. So it can't come from the Schrödinger equation. But if you check, we find that Gauss's law as an operator, little hats, commutes with the Hamiltonian. And so I can decide that the physical state of the system is one in which the eigenvalue of Gauss's law is 0, which means I can say exactly the longitudinal part of the electric field, the divergence of that, it cancels with the current J0, whatever the matter charged particles are. That just means that any quantum state where you have charged particles, you have an electric field attached to them. That's Gauss's law. So that's a choice we make. It's not something that comes out of the equations of motion, and thus we require it to get Maxwell's equations, but there's nothing inconsistent with requiring something goofier, which is that no, let's say the physical state is an eigenstate of Gauss's law, but it's not 0. There's some other garbage over here. There's some function of space. And so if there's a function of space, what would that look like? This looks like an additional source term for Gauss's law. I also don't even have to make it an eigenstate. I can say the expectation value is 0 or some function. And the point is that if you say that the physical state is an eigenstate of Gauss's law with some other value or just an expectation value, then this is the new law. It looks like Gauss's law, except there's some other term here. But then you would just say, whatever that term is, there's additional charge lying around. Somebody has put a bunch of charges around, stuck them to space-time. They're not moving, and those charges produce electric fields. So really what's happening is that the electric field is some set of quantum operators, including the longitudinal part, and we're choosing something for the longitudinal part that doesn't strictly obey Gauss's law. We're adding some longitudinal electric fields everywhere in space, and they're all just fixed and sitting there. So we would interpret it as there's charge sourcing it. Just like when you see light coming in a certain direction, you interpret that it's coming from the object that you see, even though light may have bent, come from somewhere else, or comes from infinity. So in some sense, this is an initial condition on the electric field and doesn't come with additional particles or matter. This doesn't have to be true, but I'm saying that quantum field theory does not require you to not include those states. And those are states that could live in the quantum theory.
But you cannot, I mean, can you test this with the measurement and say something? Or you're saying it still depends on the initial conditions, so you can always...
Well, you can look to see if the initial condition is non-trivial.
Right.
And I'll say something depressing about it in a minute. Okay.
Well, you're saying that there could be a fixed charge right here, right?
Yeah, it's very physical.
I can go look for a fixed charge.
Absolutely.
If I see any, I'm putting bounds on this.
That's correct, yeah. Yes. Kind of fixed, yeah.
Well,
Before we talk about gravity, yes. Okay. Let's talk about gravity. People panic about gravity and quantum gravity and things like that because everybody's told that it's terrible and nobody understands it, and only people at the Institute of Advanced Study is allowed to work on it. So I don't subscribe to that. And also, the important thing about gravity is that it has many regimes. There is the center of a black hole. That's a place where GR itself breaks down. So we don't know what goes on there. And quantum mechanics gives us a scale at which singularities have to turn into something else, or should. We also talk about gravity in cosmology, and it's totally classical. And you would naively think that cosmology should be very simple and healthy and easy because it's at long wavelengths. It's not at the Planck scale. So whatever the quantum theory is, it should spit out the classical theory in some way. But it turns out there's a little bit of weirdness about that as well. So let me do gravity in the simplest form I can in 4 dimensions, which is mini superspace. Mini superspace is, let's only look at the homogeneous evolution of the universe. So FRW cosmology. How would we construct the quantum theory of that? So naively, the metric you would take is just a scale factor. There's just a G00 and a GII piece. Because it's isotropic and homogeneous, this is a function same for all 3, and it only depends on time. And then G00 can be some arbitrary function, also only depending on time. And now what we would do is we would write the full Einstein-Hilbert action with extra crap to get rid of surface terms and things like that. And then a matter action which couples to gravity, and we'd get, in the general case, naively all the equations of motion of gravity. And since the only metric we're putting in is a scale factor and this other function n, then when we vary the action to get a minimum, we just vary n and we vary a, and then we'd vary the action with respect to whatever matter fields are there. And the first variation gives us, in fact, the first Friedmann equation, which is, here's Hubble squared right there. And the second variation with respect to A gives us the second Friedmann equation with A double dot. And then this variation with respect to matter fields gives us equations of motion with matter with things like Hubble friction sitting in there. So this is how we can derive Einstein's equations and regular matter coupled to gravity from a classical action. And so if I want to go quantum, I want to build the Hamiltonian, and there's a procedure, which is I have to identify the conjugate momentum. And in the same way as electromagnetism, some of the fields, in this case n, the time derivative n doesn't appear in here, and so there is no conjugate to n. Whereas the matter has conjugate momenta, and the A, the scale factor, has a conjugate momentum. So when I build the Hamiltonian, I switch from A dot and phi dot to pi a and pi phi. This is my conjugate momenta. But n I have nothing to do with, so I just leave it alone. And what I discover is that the Hamiltonian is a function of a, phi, and their conjugates, all times one single power of n. That's the only place n appears. N is called the lapse function. But that n should be there, because what is Schrödinger's equation? It's this, as we've constructed it. And if this is Schrödinger's equation, you notice that that n can be slipped over to the other side. And so in fact, this quantity, n times dt, is the time differential. It is proper time. So that n is there only to say I can reparameterize what I mean by time. So it's that extra, you could call it a gauge symmetry. It's an extra freedom which is not physical. It just tells me how to label either fields or coordinates. So in the same way that I pick a gauge in electromagnetism, I can do it here to ask physical questions. And again, the simplest gauge I will choose, which is n equals 1. And when you do that, all that's left on the gravity side is A and its conjugate. And so just like in electromagnetism, I can get one of the equations of motion. And when I switch out pi's for their AA dot analogs, I get the second Friedmann equation. The second Friedmann equation is a dynamical equation, has a double dot in it. And it is a consequence of Schrödinger's equation. What about the first Friedmann equation? Actually, that's a lot like Gauss's law. It's something which is, when written in terms of conjugates, it's not a dynamical equation. And in fact, the first Friedmann equation came from varying the action with respect to n and setting it to 0. If I write the action in terms of a Hamiltonian, what I discover is that the Friedmann equation, the first one, is just that the Hamiltonian is 0. That's called the Hamiltonian constraint. It is actually just the Friedmann, the a dot over a squared equation times square root of g. So in the standard treatment, what would we do? Like in Gauss's law, you might want to say that the physical states of the theory are annihilated by h, so that all the physical states have h equals 0. But if this is a quantum theory, that doesn't make any sense, because that means there's no Schrödinger equation. It just means trivially that states don't evolve in time. And so if you assume something is, maybe this talk seems like it's going very long and it's not evolving in time, but in fact it is. So there's something wrong with this, and this is often called the problem of time for quantum gravity in the canonical language. There's a simple fix, which is just don't impose this, just say the initial condition is that the expectation value of h is equal to 0. Whenever we do the classical limit of big floppy fields, we are in coherent states. Those are states that have expectation values for the values of the fields. They behave very classically. They have very tiny uncertainty in their value. But they're not eigenstates of the fields. They're not eigenstates of energy. And a laser is a good example of one of those. It's a coherent state of the electric field. You can derive it from a quantum field theory and get a classical wave. So in the same sense, what we want for gravity, perhaps, is a coherent state, because the metric is big and floppy. And so it shouldn't be an eigenstate of all the fields or the Hamiltonian itself.
Can I ask, so why did I get rid of n? I mean, why didn't I use that as a constraint? As a Lagrange multiplier, sort of?
Yeah, so you can derive the path integral, leaving n, or putting n back when you get the path integral. And then when you derive the path integral and you vary with respect to n, you do get, in fact, the Hamiltonian constraint. And then you ask physical questions, which is, okay, I want my path integral to time evolve some initial wave function. And you can ask, what is the result of the time evolution of an initial wave function? And you discover it doesn't evolve. That constraint forces you not to evolve anything. That the remaining basis is one in which things don't time evolve. So you can look at a path integral, gravity, action, blah, blah, blah. You can do that. And as long as you integrate over n as a Lagrange multiplier and put the constraint on initial states, you get no time evolution. Now, people mess with that in a couple of ways. So one is that if you do perturbative gravity, like an S matrix calculation, gravitons coming in, going out, you can mess with the initial state. You can define the Hamiltonian at infinity as being uncertain. And that is the cheat people make. You can add an arbitrary constant to the Hamiltonian, and then you can define scattering. And that looks like a time-dependent process. But it's because you've cheated, you've done something to the initial state that violates this constraint. And the other cheat you can make is in ADS. ADS has a boundary with no gravity on it, and you can similarly put statements about what the initial and final or boundary conditions are for this thing. And then for ADS, therefore, you can have the uncertainty live just at the boundary. And so you can have global uncertainty in the Hamiltonian. And then in principle, you should be able to get time evolution in principle. So those are the tricks. It doesn't allow for linear combinations of different cosmologies or things with different boundary conditions. There's no good way to do it in FRW. So it's an ongoing debate. People also think about the possibility that time doesn't come from the Schrodinger equation. It comes from something else. It's some part of the state. So the state is a clock and everything else somehow. You could split that up, and the clock is entangled with everything else. It doesn't tell you why time evolution solves the Schrodinger equation in the naive way, but it's a guess, and then people write all kinds of crazy papers about that the state of the universe is a linear combination of the universe at all possible times. Then it would be time translation invariant. But I don't think there's a clean, solid, general cosmology limit of quantum gravity. That's my sense.
Sorry, can I ask? So you're saying people doing perturbative gravity calculations, no? You're saying they add a constant to the Hamiltonian?
At infinity, essentially, yeah. An arbitrary, uncertain constant. So, yeah.
Are you saying that's not justified a priori, but maybe then, so then you compute whatever you have to compute?
No, it's just I don't believe in this anyway. So I think what they're doing is correct. I think that's probably how gravitons evolve. That's my guess, that's how they evolve.
But you're saying, but that's not a good way of understanding why you do that?
Well, you get to skip over this problem.
Yes.
I mean, this problem really is about can the state of the universe be in FRW1 plus FRW2? Is that allowed or not? So there's no way to construct that in this language, but then you can decide if that's true or not. I think that's it. The boundary is also funny too, because in a sense it tells you what gravity is asymptotically. So it's almost like the monopole. So you can have a lump and not know what its mass could be uncertain. And so but that's the asymptotic value. But if you have some complicated state, you only have the asymptotic value that has nothing to do, you wouldn't want it to have nothing to do with local things. And you can say fancy things like holography, blah, blah, but I'm suspicious. Yeah, anyway. So and it's considered still a problem with canonical gravity. Even people at the Institute are worried about it. Ed wrote some paper which was about the canonical gravity in December of 22 and didn't understand it and said DeWitt doesn't make sense and the Hartle-Hawking wave function is wrong, and then it went into like 30 pages of math gobbledygook that I did not understand. But I didn't see a conclusion at the end of some physical revelation. But yes, in the pedestrian world that I live in, one can just do this, and when you do that in expectation value, you get the first Friedmann equation. And whenever you go to the classical limit, you are assuming something like coherent states, that commutators don't matter very much, that these are very classical states with small uncertainty. And so similarly, when you say this, that's what you get in the classical limit. So now we have Einstein's equations, and we're very happy. But you could also do something goofy. There's nothing wrong with just making this some other constant. It should be a constant because h, the full Hamiltonian, commutes with itself, but that just means it's time independent. So what if you did that? Well, you just add the constant here in the classical limit, and then when you divide by a cubed, you'd get the first Friedmann equation with some goofy term there, which looks like a new form of matter that redshifts as 1 over a cubed, so you call it matter. But there's nothing there. It's just a constant term. It's a statement about the configuration of the gravitational field. Just like when you add curvature to Einstein's equation, you add some constant over a squared. It's just a source term. It's a boundary condition on the non-dynamical part of gravity. So the point is that the equations are modified. Gauss's law and first Friedmann. Yeah?
Sorry, can I answer? Would there be a way to choose your initial condition to add curvature then to the Friedmann equation instead of putting constant?
So what I've swept under the rug is when I constructed the Hamiltonian, I chose a gauge.
Yes.
If you force yourself to abide by the constraints precisely, then you get what looks like Einstein's equations. If you mess with the constraints in that gauge, so messing with the constraints now is a gauge-dependent statement, you get a certain effect. So in the simplest gauge, you get something that looks like matter. There's another gauge where it looks like the cosmological constant. And I believe that's a healthier description of what's called unimodular gravity. It's effectively setting some property of the determinant of the metric. So yeah, so what I've shown you is the simplest thing you can do, and you get a certain effect. So it's static charge, in this case, something that looks like a new form of matter that's not really there. But if you construct Hamiltonian in a different gauge, you'll get the same microscopic physics, except that your source term will be different. It won't necessarily redshift like matter. It'll do something else.
But shouldn't this be bothersome in some sense? Like in the end, whether it's matter or cosmological constant, the physical effect is very different.
It's very different.
So aren't you saying now this depends on your gauge choice?
Exactly. So more so, when you start with the Hamiltonian, and decide that that's more fundamental than the path integral, you've chosen time, which means Lorentz invariant looks a little bit more like it's emergent than I've created a structure which is the action path integral, where you put it in, it's part of the structure, it looks so pretty, so you believe it had to be Lorentz invariant. But if you start from the Schrödinger equation, why is the world Lorentz invariant? I don't know. So I'm coming from a direction where Lorentz invariance is not fundamental from the beginning. I mean, even in gravity, we don't believe there's a weakly coupled Lorentz invariant quantum field theory that produces gravity. So you could kind of take Weinberg-Witten's proof that you can't UV complete gravity with a Lorentz invariant quantum field theory. So it's something else. We don't know what it is. So this kind of language, the Hamiltonian language, gives you some interesting effects. And it might be valuable to think about where Lorentz invariance comes from as an accidental symmetry. Now, people have, for a long time, people in the margins played that game, but I think I'm newly interested in it because of this. But if that's the case, then it really depends on what Hamiltonian you chose. And
Gauge choice.
it looks like a gauge choice. That's right. That's right. Yeah, what happens when you fix the gauge, you're just deciding what the operators in the theory are. You're deciding what the Hilbert space is. Let's talk afterwards. So not everybody falls asleep, so we can discuss those details. There are lots of little details. Yeah. So all I wanted to say is that there are equations that are modified from the normal classical equations, and they are the constraint equations. We should recognize them as some statement about the initial condition and not about the dynamical degrees of freedom, the particles, the graviton or the photon. The Schrödinger equation will evolve any state you give it. So we give them a Hamiltonian, and then you can put in states that maybe you were told not to use. We're just showing that there's a broader set of states which are physically healthy, they have no instabilities, and they have weird properties, and you could put constraints on them. Now, the maybe bad news, maybe good news, these are initial conditions, and inflation redshifts all this stuff away. If there's matter at the beginning of the universe, real matter, and then there's a period of inflation, that matter is gone. So that happens to be true when you also have electromagnetism coupled to gravity. You have a fake charge density, it also redshifts away, and it's all zero. Or now it would be, if you believe inflation occurred, exponentially suppressed. It would be incredibly tiny amounts. So for the rest of this talk, I will assume that inflation did not occur, that something else set the initial conditions of the universe. Suspend your belief in the fundamental theory of inflation just for 20 minutes. Okay. Let's go to full general relativity. In pink are the equations that are important, and the rest is mostly ignorable for your benefit. So classically, again, it was discovered that one can write down an action for gravity. It's the same action as before, but now I'm allowing space and time to all vary. And when you vary the action and demand that it varies with respect to all components of the metric and that it's equal to 0, you get Einstein's equations, or times square root of minus g. And now you say, I want to build a quantum theory, so let me get the conjugate momenta. So the conjugate momenta for the spatial Gij is fine, because Gij dot, the time derivative, appears in there. But G0 mu, G00 and G0I dot do not appear in the action. And so there is no natural conjugate momentum for those. There's a whole fancy language of how you're supposed to or required to address these sorts of issues. It's the Dirac quantization conditions for theories with constraints. It's a whole set of rules. I come from the attitude that we don't quantize classical theories. We try to find the quantum theory that spits out the classical limit that we are interested in. So I will just look at that and say, fine, no conjugate momenta, who cares? Let's just set the gauge. And in gravity, because there are 4 coordinates, you have 4 functional freedoms. So I can fix 4 components of the metric. And this is called synchronous gauge. Synchronous gauge is nice because G00 is -1. And G0I is 0, which means time is independent, doesn't mess with anything else. It's a natural gauge in which to quantize. You don't have to, though, but it is a useful gauge to illustrate something interesting. We'll call the spatial metric gamma ij, so when gamma appears, you know it's just the spatial. And now we have the metric pieces and the conjugates, and we're just going to require the dumb commutation relations. You can construct a Hamiltonian, which you get from the Lagrangian using this standard procedure. And it has the conjugate is like a kinetic term for the metric, and that is spatial curvature in 3. And now you ask for the equations of motion, and we use the same trick, which is effectively Schrödinger's equation, and you get only the spatial parts, which you would have expected, because we only have the spatial parts of the metric. And the remaining equations are constraint equations. There's the 0, Einstein equation and the 0I Einstein equation. And we can set those as constraints by saying the expectation value of that function is 0, and those functions are 0. These are called Hamiltonian and momentum constraints. And then you could do something goofy, which is, well, why don't I just make this some other function? I don't know, something else, and that too. I don't care about your constraints, I'll just do something else. So if you do that, it's effectively like saying these equations, you can make an equation wrong by just adding an arbitrary thing at the end of it. Now it's just wrong, but I can parameterize how wrong it is. And there we go. It's 2 arbitrary functions at this point. But of course, Gij, G0I, G00, they're related to each other. They're functions of the metric variables. And so that relation is important. First of all, I can reconstruct the tensor language, and I can write G mu nu in the normal way, Einstein's equation, and put all these guys together, collect them into a tensor, just define the tensor. That tensor has a particular form in synchronous gauge, which is the gauge we chose. So here is this new source. It looks like stuff. And in addition, because there's a condition on the Einstein tensor, which is the Bianchi identity, this is just an algebraic, I mean, they're derivatives, but this is just effectively an algebraic condition. And the equations of motion no, you calculate this. You could, if you wrote a path integral and you asked what this function does.
No, I'm doing you a Hamiltonian.
Yeah. If you take the classical limit, meaning you don't care about commutators, then this is just true.
Including the new components that you added.
Yeah, this is it's just a relationship between these 10 functions. They're just algebraically, this just algebraically cancels. This is 4 equations, and you write down those 4 equations in terms of the metric, and you get cancellations. This isn't dynamical, it's not something imposed in gravity. It's just G mu nu, capital G mu nu, is defined in terms of the metric and derivatives.
It's giving you a new constraint here, no?
So this, yeah, so good. I thought this was confusing. Okay. So this is an equation that we get out by hand. And now I'm saying that these 2 equations are not satisfied. And so I can define some crap here to say that they're not satisfied. And then I can ask, so this is some combination of the metric, this is a combination of the metric, and this is, I can ask, is there a relation between GI and G0? There is yes, which is a mathematical relation. It's not true. There's no such thing as gravity, but I just construct G mu nu as an object. Component of it, divergence of it, classically it's 0.
Yes, but now with the H and the P added.
I'm removing all of this. I'm telling you Einstein's equations are not true at all. There are no Einstein's equations. There's no gravity. I'm just giving you a mathematical object. So I'm saying is that that object has this property, that these aren't linearly independent, or not really linear, but yeah. So that's what's happening. Yeah, so this just told me that the source terms that I could add here are limited. It's similar to electromagnetism in the sense that I can add something to one component, and that component has to be time independent. So the charge density I add has to be static, time independent. You can get to that conclusion in a similar way. You discover that from the equations of motion, charge is conserved. So if you had, F mu nu, d mu F mu nu equals J mu plus the new but we can take some limit. For example, we can just let ignore the off-diagonal terms. If we do that, we find from those constraints that h is constant. And so the only thing that's modified is there's something in the G00 equation. We can write that tensor in a fancy way by making this a tensor, a scalar, and 2 vectors. It's just a matrix with one eigenvalue that's non-zero. So I can construct it in this way. And what I discovered, this object, if it's covariantly conserved, it just looks like a pressureless dust. This source term just looks like that there's some function of matter and there's some 4 vector which we might interpret as the 4 velocity of this fluid. Too technical, but for regular dark matter, you can prove in synchronous gauge that for regular dark matter, the most general form of a dust is, in fact, some function of space divided by the square root of minus. Where you absorb the remaining spatial degrees of freedom. There's a remaining spatial coordinate transformation that allows you to turn h bar into a constant. And if you do that and you look perturbatively at the F or W metric with the little perturbation and you calculate the size of that perturbation, you can relate it directly to a perturbation in the 0, 0 component of the shadow tensor, which is to say that this object, at the linear order, you see immediately, if you do cosmological perturbation theory, that it just acts like dark matter. Now, we could perturbatively expand, say that h bar is a constant. Let's put back this in h, make it perturbatively small. And now let's add a little bit of pi. Pi, it's a vector, so it's not isotropic or homogeneous. But if we expand around homogeneous and isotropic background, treat this as a linear order perturbation, then you can ask from the constraint equations, how does this one behave? And you discover that a squared delta p is time independent, which means that or even radiation. Perhaps matter, then this extra term would be expected to live in the smallest bound states, the ones that formed first. Now, in general, if you have both h and p source terms, you have this weird mess, but you can rewrite this T mu nu tensor as rho u mu u nu, looks like some matter, plus these strange terms, which in the literature are called heat flux terms. And they are not like a homogeneous isotropic pressure, so this is not a normal perfect fluid, it's something else. And so this physically distinguishes it from dark matter. The issue is if it's small, it could have redshifted away much more quickly. And then you can do crazy things. Since h can be positive in some places and negative other places, that's effectively like negative mass particles floating around in locations. And you can ask, what bad things does that do? We have a guy doing simulations for us. It doesn't seem to do anything bad. I mean, the only bad thing that it does is it's hard to tell the difference. So these conditions. And then the last thing I want to say is that if we go back to electromagnetism and we add gravity, yeah, sorry, hey, Patrick.
Are you to do the perturbation theory for the GR part? I mean, you're positing homogeneous and isotropic cosmological background,
Yeah,
but you're also not having inflation.
that's right, yeah.
Okay.
Yeah, so one can ask, where does that come from? In other words, if you want to explain that, you need something else in the story. So one possibility that people think about is a semi-static universe that maybe transitions into expanding universe. So if instead of super fast expansion, you have very, very slow or negligible expansion for a long period, the universe homogenizes because it now has time to do it. So that sort of initial condition would do it. And then you can, the real question is then, why do you get a flat spectrum? This explanation for dark matter, which is it's just an initial condition. It's just another source term. Like curvature would be, or that the cosmological constant is. And so you have to choose. And you can check to see if you can make the initial conditions nicer in this case. Yeah, so the last thing I was going to say is that if you have electromagnetism, you violate Gauss's law, meaning you allow yourself to write source terms. Then you discover that when you attach it to gravity, it also redshifts in the same way. So it looks like, not only does it redshift, it behaves exactly the same way as the shadow matter in the sense that it follows geodesics. So you can write it in synchronous gauge and trivially show that this charge follows geodesics. Which means if there's some background matter in the universe, or dark matter, or even that shadow matter, and you add this stuff follows the dark matter, it's charged, it does not respond to electromagnetic forces because it's not charged particles, it's just longitudinal electric fields. And thus this adds a Okay, so shadow matter is the result of starting from a Hamiltonian description of electromagnetism and gravity and not forcing the constraints as we usually do. You can still get a consistent quantum field theory, and the classical limit makes it look like there's a new type of matter that follows geodesics, has no pressure, and doesn't respond to other forces, which maybe that's the dark matter. And then there are new source terms for electromagnetism, and that produces a charge component of this fake dark matter. It could affect CMB, BBN, galactic dynamics, or structure formation, direct detection. It's challenging to understand the phenomenology because it's effectively like adding infinite mass ions to the standard model plasma that don't gravitate. And so one has to figure out what happens to the plasma dynamics. In that case, how does screening work? What happens when it hits an object? So there's fun things that we're trying to figure out how to do. The new source terms could be crazy. They could violate the null energy condition. We're okay with exploring Thank you. Yeah.
Is the initial condition for dark matter somehow related to the initial condition for the cosmological constant, or?
It's not. I mean, it is in some sense, which is that I've chosen the Hamiltonian, and once I've done that, there is a set of constraint equations that I can satisfy or not. And in the gauge I've chosen, those constraint equations become matter. But there's another way I can construct the Hamiltonian where matter behaves the way it should, but there's an initial condition that is not necessarily satisfied. But that initial condition looks like a cosmological constant. Now, there are 4 initial conditions, and I haven't gone through it because it's just a bit of a technical mess. But the sort of 0th order initial condition is a cosmological constant, and then there are sort of it's a natural order theory. So it's like you choose one. Basically, you so in the homogeneous case, you always get some equation that looks like this, P, and then you could have plus some amount of rho. And that depends on, in the metric, what you did with the lapse function. So I set the lapse function to 1, you can set it to A, you can set it to 1 over A cubed, you can set it to some power of A. It's just a decision about what to make that object. So in electromagnetism, it's like Coulomb gauge versus Weyl gauge. I can make A0 an integral of the charge density operator. I can make A00. I can do whatever I want. So if I do that here, it has non-trivial consequences, and the dynamical equation depends on some linear combination of pressure and density. And then the simplest gauge I chose, it was just pressure. So anything with pressure generates the standard dynamics, but something with 0 pressure doesn't have it. If
That's what you said in the...
yeah, if you want if you decide that this beautiful theory is the explanation for dark matter, then dark matter comes from a statement about the initial conditions of the metric. It behaves like dark matter, which means it redshifts like matter. And so if there's a period in the universe where the dominant energy density is a cosmological constant, like inflation, then that initial condition redshifts away. So it will be left over, but it'll be exponentially suppressed in density, and it won't play an important role. So that's the conflict.
So for the last part with the charged subcomponents or whatever, I sort of understand how maybe it might work during radiation domination. But you say something about like direct detection, and so you think of it as like a monopole or something, or like a charge?
More like millicharge stuff. Yeah, I mean, so people come up with direct detection ideas for normal millicharges or parts of so is the disk, but that stuff is moving like dark matter, so it moves into the halo, back in, it does stuff like that. And what happens when it hits the atmosphere? Then maybe it ionizes or it sheds some of that, depends on the depth of the potential. And then now you have something that looks like charges moving through, which is just like some kind of wave, electromagnetic wave moving through. And in principle, you could detect that. Very hard to detect electric fields.
It's just like a really, really weak heavy charge. Like,
Yeah.
it's like lowly ionizing but massive.
Charge to mass ratio is extremely small.
Yeah.
Exactly. And so it's just plowing through everything, and it's not stopped by matter. And then can you detect that current, basically? And yeah, so that's it. I don't know, yeah, but it's hard to determine what it, so we have to settle on the initial condition we like, and so we had a crazy idea. Okay, I'll take responsibility for this one, but if you say dark matter is just a bunch of and then the voids were screened by antiprotons. In other words, could you not have a baryon asymmetry, but you could have a distribution of charge asymmetry with the structure of matter, and then we're hiding the positrons and antiprotons by these screening fields. And so we've turned off, it works in the opposite way. You violated Gauss's law by a proton or an antiproton not having a field around it. So can they be trapped in these fields? So that's a thought. I don't even know if the orders of magnitude work, but that's an unusual effect that you could potentially have.
Unusual kinds of constraints from like pair annihilation or like, because people have thought about things like that.
Yeah, absolutely. So you have to ask what density of non-effective, non-electric field responsive positrons could you have in the galaxy, or is it better to have antiprotons in the galaxy? So you get to choose the sign. Yeah, so I don't know what the magnitude is. And in that case, yeah, so there's that possibility. Also, the dark matter could be regular matter, but it's so the point is, if I design this screening field just so that some charged particle here, positron or electron, the field exactly cancels the Coulomb field of that particle, then this cross section is 0, except maybe for the weak interactions or something like that. So you can tune it to make it look good, but I suspect for a general case there will be bounds on that, and I don't know if it will be more interesting that they're screened regular matter scattering off each other, or just the bounds of this component of charged dark matter scattering off of the gas in the bullet cluster. So one thing that that bumpy field will do, it could cause Bremsstrahlung, it could cause, because you're now scattering off of these background fields. This lump doesn't have to have quantized charge, so small lumps could, a quarter of an electric charge, something like that. So yeah, this problem is there's an infinite number of things you could do, and we're trying to think of what are missing. So but not precisely 0. because they're following matter geodesics, but they don't interact other than gravity. They follow geodesics. They're zero mass, so it's a continuous